Good afternoon. Okay. My name is Kai Staats. I'm a researcher at the University of Arizona, and I work principally at the Biosphere 2. And my team is building a high fidelity Mars, Moon, and Mars analog called SAM. So today I will be presenting to you a little bit about the history of the Biosphere 2, which of course was the world's largest and longest running sealed analog and a habitat analog. And I'll also be talking about CMAC, which is a computer model that we've developed that will be working hand in hand with SAM, with our analog. So I'm going to turn off my video and switch to my presentation. Just a moment. And here we go. Okay, can you see my screen?
Yes.
Okay, great. Okay, there we go. So again, the principal presentation is about SAM, which is a space analog for the Moon and Mars. And I'm going to give you a brief history of first the Biosphere 2 and how we came into this project, but I want to ask a first fundamental question. This is the question that we are working to answer as a scientific process and also as a process by which we are inviting and working with researchers from around the world in our Mars habitat. The question is, of course, what is the minimum complexity required to sustain human life on another world? I think we're all trying to answer that question in some respect, and there are many, many different ways to approach the solution for this problem. And so the first thing I want to tell you about is CMAC. So CMAC is a scalable interactive model of an off-world community. This is a research-grade computer model that I began to develop at Arizona State University in Tempe, Arizona in 2017. I had funding from Arizona State University for 2 years, and this started as an undergraduate computer science project. So I had students from an undergraduate program for 2 years working with me, and we started with this, by the way, is the workflow diagram from Lunar Palace 1, which of course was the University of Beijing's fabulous project on a fully sealed environment. This is their nutrient flow diagram, which many of you have seen this before. This shows the movement of the plants and the atmosphere, the crew's digestive process, the waste process, how do we reclaim the water, including the consumption of yellow mealworms, which is a fantastic way of taking inedible biomass and converting it back into something that humans can consume again. We started with diagrams like this, trying to understand the minimum complexity required to sustain a fully sealed or at least a fully bioregenerative environment. And I developed my own diagram. This is the CMAC agent interaction diagram. I recognize you won't be able to see all the details here, but I want to give credit to Ray Wheeler, Dr. Ray Wheeler, who built this diagram. He's from the NASA Kennedy Space Center and has spent his career in working in plant physiology of closed ecosystems. A fabulous individual with a wealth of knowledge. You can find him all over the internet. Again, Dr. Ray Wheeler. So if we zoom in a bit, we looked at the details of how these agents in our model, our computer model, would interact. And so we looked at everything from communications to water flow to airflow to recycling to each of the built environments, including a clinic, a rec center, the sanctuary, the kitchen. We looked at every aspect of what might become someday a very complex and rich habitat environment on another planet. We then engaged those. We developed those agents in this model and defined them based upon existing data. So we use the NASA's, it's called BVAD, the Baseline Values and Assumptions document, which is built upon 40 years, 50 years now of data collection from all of NASA's experiments. So if you haven't seen this before, you've got to download it. It's a free publication called BVAD, B-V-A-D. It's available from Google Scholar. And it includes everything you can possibly imagine. How much carbon dioxide does a human consume when sitting, when sleeping, when running, when eating, when doing yoga? And how much oxygen do they need? How much water do they need? And how much are they putting out again? So this data is invaluable. We took this data and put it into our computer model as discrete components to define the human agent. We have over 50 agents in the model, including including the structure itself, the building, the CO2 scrubber, the lighting, the computers, and all of the plants. So again, working with Ray Wheeler's research, we have 22 plant cultivars, and we took his research and defined it again as individual agents, one for rice, for wheat, for cabbage, for chard, for celery. We have the starting weight of the seeds. We have the final weight of the harvested material. We have nitrogen, potassium, phosphorus, water vapor, atmospheric oxygen, and carbon dioxide. And again, each one of these are simulated on an hour-to-hour basis in this simulation agent. What I find fascinating in a longer presentation, I've actually brought a bag of groceries into a room when we were allowed to get together in rooms, and I'll hand out the groceries at the beginning of the presentation, and I'll hand out cabbage and strawberries and a loaf of bread, and also potatoes and onions and tomatoes. And I'll just go through my talk, and at the end of the talk, I ask people, which vegetable would you like to bring to Mars? And then I show this slide and I say, well, let's look at the differences. You know, the cabbage, we can eat almost the entire product, the edible and total inedible. We're able to eat all of it. Strawberries, not so much. Wheat, we can eat roughly 1/3 or a little bit over 1/2 of the wheat. But look at the CO2 sequestration. The amount of CO2 that wheat absorbs or consumes is considerable. It's 2.5 grams per hour, whereas a strawberry is only 0.79. And then we look at the sweet potato as 2.5 grams per hour, and the onion is significantly less. So this matters. When we go to Mars or to the moon, when we start to establish greenhouses and we rely on those greenhouses, not only for our food, but also for our bioregenerative properties of our air and water, it's important that we choose the vegetables and fruits that serve as many purposes as possible. So wheat takes 3 to 4 months from, well, I think it's 120 days from planting to harvest. And because we are not ungulates or bovines, we do not have multiple stomachs, we are unable to consume the wheat directly. We have to process it. Whereas a sweet potato, we can eat directly out of the ground. So if you have a choice, you're going to want sweet potatoes. So then we built an interface, a web interface for the users to CMAC, where you design your habitat, you choose the plants, you choose the astronauts, the number of CO2 scrubbers, you choose your solar panels, your batteries, and you set this in motion. Now, I'm going to wait and actually do the live demo a little bit later. I want to make certain there's time for questions. But this project is now hosted by National Geographic Society. It has been for the last year. As of 3 days ago was our 1-year anniversary. So we've been proud to be partnered with National Geographic. They are providing funding and also the platform by which CMAC is available for free to everyone in the world. And CMAC comes with a full curriculum for grades 5 through 8 and 9 through 14. There's demonstrations, there's video tutorials. It's a rich, dynamic environment for those of you who are instructors in classrooms, virtual or physical. I encourage you to give CMAC a try. Okay, so CMAC brought me to SAM. SAM is the physical representation of CMAC in the real world. And that's what I'm going to talk about now. So this is Biosphere 2 as it exists today. Those mountains behind are the Mount Lemmon. It's a beautiful, beautiful environment in southeastern Arizona. Yes, we have snow in the desert. People think we're just hot cactuses, but we actually have a diverse range of ecosystems or environments within the desert here. So this facility was built by an incredible team of people back in the 1980s. It was started in 1987, and the first experiment ran from 1991 through 1994. To date, it is the world's largest and longest running sealed experiment in bioregeneration. 3.5 acres of land beneath a single sealed building. When this was operational, the amount of air that leaked day to day from this 3.5 acre structure is less than the International Space Station today. It was a fabulous invention, incredible invention, and it operates today not as a sealed experiment, but as the world's largest indoor science experiment in plant ecology. So there's a rich, dynamic array of science experiments running within this facility today. There is an ocean. the world's largest experimental saltwater ocean contained within a building, and including a wave pool, a wave generator that's been running for 30 years continuously. And right now they're rebuilding the coral reef. They're experimenting with clams. They're introducing new fish. It's an incredible place with live interactive environment for researchers. There is a rainforest, and the rainforest is the only place in the world where you can experiment with the plant ecology of a full rainforest. You can actually go underneath the rainforest and work from the root level up or the tree level down. And there's also a full savanna and desert space within the same canopy. And all of these spaces are connected by a simple walkway. So something I want to share just briefly is that while the 8 biospherians were living inside of this facility, they struggled with a number of very real world challenges that we've learned from, and we should thank them for these things that they learned, because we'd rather learn them here on Earth than learn them later on Mars. You may have heard that they struggled with oxygen, and the reason was because the cement, the concrete, was poured, and just the same, within the same time frame when they moved in. It takes years for concrete to dry, and the chemical process by which that happened pulled all the CO2 into the concrete and thereby reduced the amount of CO2 available for the plants to produce oxygen. A very difficult process, but we've learned a lesson. Also, they ate a lot of sweet potatoes. They ate so many sweet potatoes because of the immediate nutrients and satisfaction of the sweetness that their skin turned orange from eating so many sweet potatoes. I want to share with you one technical aspect of the biosphere too. This is the south lung. There are 2 of these lungs. Inside, these are giant geodesic domes, and inside that is a 40,000 pound slab of steel and concrete, and it is floating on the air. This is not magic, it's physics. So the air pressure inside is about 0.2 of a PSI higher than the outside, and with just a 5 horsepower motor, you can lift 40,000 pounds. This is basically the buffer that enabled them to do what they did for 2 years. There are 2 of these lungs, and these lungs provided the constant air pressure, the positive air pressure for that hermetically sealed environment, as well as a buffer such that as the atmospheric pressure changed on the outside, the integrity of the windows were not in question. They were able to sustain a positive pressure independent of pressure changes outside. Valuable lesson learned, and incredible engineering. So in 1987, 4 years before they moved into the biosphere, the same year, or actually before they started building the biosphere, they built the test module. The test module is about 250 meters east of Biosphere 2 on the same property. And this was not the first, but one of the first bioregenerative sealed environments. There was three full experiments that were run in here, one of which was with Linda Lay. She stayed inside for 3 weeks, completely isolated from the outside world, all of her air, all of her water, all of her food provided by the plants inside. This is the cornerstone of our project SAM. We've been given this facility. It's still standing, it's still functional, and we're rebuilding it to make it functional. So we have a full ½ acre of the test module, plus a full Mars yard that we're developing adjacent to that. So we're proud to be starting with such a historic and iconic structure. And this is a little bit about the structure. You can see to the right, there is also a lung. We have our own lung, just like the one I showed you, that provides automatic pressure regulation system for the test module when it's sealed up again. So in January of this year, my partner Trent and I, we started work on the test module, and we had 30 years of desert to take away. There were rats and mice and squirrels and scorpions and rattlesnakes and a lot of desert plants. And so we've been grinding, and we've been painting, and we've been wiring and cleaning and working on this facility now for 4 months to give it new life, to give it a new opportunity. And so it's been a lot of work. We've been working up to 18 hours a day, 5 days a week for 4 months. We've had volunteers come from all over the United States, even from Peru. And we've been, as I said, cleaning and grinding and painting and applying new window film and such. Each step of our process has been driven by a scientific endeavor. So when we, for instance, applied the window tint to the windows, as you can see in the bottom right corner, we chose window tint that reduces the amount of light coming into the facility by 50% to represent the ambient light on Mars. When we choose our paints, we are choosing paints that are approved by NASA as zero VOC paints, so we are not chemically infusing the atmosphere inside with something that's harmful to the inhabitants. We have also conducted our first full pressure suit test using a pressure suit from Pacific Spaceflight and Smith Aerospace Garments. Seated in this upper left is John Adams, who is the Deputy Director of Biosphere 2. He's been at Biosphere for 26 years, and he had the pleasure of putting on a full spacesuit and conducting tool use and a test walk around the facility, all of his air provided through an umbilical cord. So we have 2 of these spacesuits being manufactured for us. They'll be available, they'll be ready in about 3 weeks. And everyone who comes to use this facility as a research team will have an opportunity to conduct full EVAs in a pressurized suit, having exited SAM through an actual airlock. So this is about 3 weeks old, the photograph. There's a little bit more that's been done since then on the outside, but you can see how much we've improved the facility and increased the fidelity. You'll notice that on the roof structure, it's now white instead of glass. We painted it with silicone. The reason is that while we do not have the ability to bury our greenhouse as you would on Mars, we at least simulate the protection from the radiation from above. We have the benefit of overhanging windows, which represents a clear view to the horizon without direct radiation. And so again, we've reduced the ambient light coming into our greenhouse structure in order to simulate what it's going to be like on Mars. We will have to use synthetic lights to grow our plants. That's exactly what will happen on Mars. There's not enough ambient light to grow most food cultivars. And to the right is the lung. It's a small lung, but it provides all the pressure needed for the habitat. So this is an artist rendering without the silicone on the roof of what our facility will look like in the future. This is an artist rendering of the interior space of SAM, of the test module, I should say. And we're also adding 1,200 square feet of living quarters, of living space, composed of 3 shipping containers that'll be welded together. Again, one of our first designs for the use of this space. And this is the greenhouse structure that is next to SAM, and this will become our Mars yard, or one of our Mars yards. So we'll have an indoor Mars yard and an outdoor Mars yard. The indoor Mars yard is going to include a 6,400 square foot, about 1/4 of an acre or 1/8 of an acre simulation of a Mars crater. We just received our first selection of human on Mars landing sites from NASA and Arizona State University. We'll be producing a scale model of that crater within this building, down to the details. So as you exit SAM and you leave the airlock in your pressure suit, you will be on Mars. There's going to be a lava tube and a gravity offset rig, such that when we attach you to a cable, and we can reduce the apparent mass of your body to whatever number we want, 1/2, 1/3. And so you will actually experience what it's like to walk on Mars with reduced weight. So I want to cover, in closing, I want to cover the 5 principal science objectives of SAM. We are, now these are not limiting the research teams. This is what we're interested in. The research teams that come to SAM, of course, will have the ability to work on whatever they want, as long as it fits within the confines of our space and is safe for those participants. We are looking at a transition from the physiochemical to the bioregenerative life support systems. That means that we will start with machine-based life support and transition to bioregeneration. We do not expect to be 100% bioregenerative, but we do expect to have a hybrid between the two, which is very realistic for what we'll have in a 3rd or 4th generation habitat on Mars. We'll be working to transform simulated regolith to soil, starting with crushed basalt from the volcanoes of northern Arizona, laced with perchlorates, and then we'll be removing those perchlorates using mechanical and chemical and biological means. We'll be studying the microbiome of the built environment. If you've read anything about the space station, you know that it is rich in a microbiome. There are fungi and films. There are a lot of living creatures there that are beyond the humans, and we need to understand those if we're going to live in these environments for long periods of times. They can wreak havoc on the mechanical systems, even the computer systems. We're going to be using pressurized spacesuits for all of our entries, exits, and EVAs. And back to CMAC, as I opened, we'll be using advanced computer models for the simulation. For those of you who have a science background and training, you will recognize the value of a computer model that has a real world implementation where those two feedback and support each other. So we'll be integrating dozens of sensors within SAM such that that data will go to further advance our computer model. Our computer model then will improve so we can more closely predict, more accurately predict the function of SAM. And ultimately, we would like CMAC to be able to operate SAM using an artificial intelligence algorithm such that it can actually maintain a lot of the functions of SAM. That's our long-term goal. And key features in summary, as I've shared with you, we're building on the legacy and experience of Biosphere 2. Some of the staff at Biosphere 2 have been there for 30 years. So we have their experience, their expertise, and we have the University of Arizona just down the street. We have a controlled greenhouse environment. We have a living quarters. We have an on-site mission control center with accommodations for 6 crew. There's 3 bedrooms, 2 bath, very nice environment right there on campus. So when you come as a team to stay with us, you can have up to 6 mission control center people, and you can rotate with your 4 crew members in SAM about once every 4 to 5 days. The team will select whether you want regulated airflow or hermetic seal. There's going to be use of airlocks. The Mars yard, as I said, will have a crater, a lava tube, and a gravity offset rig. And of course, we will be working on computer models. You're welcome to bring your own computer models as well. So there's more information, a rich website with a complete photo essay of every week that, sometimes every day, but every week that we've been working on SAM. There's a full set of stories and all the science that we're conducting, even in the construction of SAM. And of course, CMAC is the computer algorithm. And I want to give thanks to Biosphere 2, to the University of Arizona, to National Geographic, to Paragon for our CO2 scrubber, and to NASA for all the support that we've enjoyed in the last 6 months of working on this.